Welcome to EDU World Space.
So Q is the total charge of the uniformly charged insulating sphere, and R is the radius of the sphere. So the magnitude of the electric field can be defined by the following equation. So E is equal to 1 over 4 pi permittivity of free space times QR over the radius cubed. So the radius of the sphere, cubed. So this is when the radius, so it's inside the sphere. And when it's outside, it can be defined by the following. So E is equal to 1 over 4 pi the permittivity of free space times Q over R squared. So this is when it's outside the sphere. So now let's let VR equal the electric potential inside the sphere and distance R from the center of the sphere. So this is when R is less than the radius of the sphere. So then let's go ahead and write that equation. So the potential R is equal to the integral of R from R to A times EdR. And we know that we can, since this is inside the cylinder, we can replace it with the first situation. So here, so let me just bring that down over here. So here, and it is integrated with respect to dr. And now we also know, I'm missing something here. I just realized. So let's move this back. Let's move this back up here, since I am missing something. This is R cubed. So this is equal to EdR, but we forgot the distance from R to A. We can actually split this into R to the outside of the cylinder. So this is the surface of the cylinder, and this is also EdR, plus the integral from the surface of the sphere to the point outside, and this is also once again just EdR. So now if we can replace both these by the above equation. So now let's go ahead and bring them down. So since this is inside the cylinder, and as we stated previously, this fits our conditions. And once again, this is dr, integrated with respect to dr. And now we can also replace this E with this following second, with the second expression here. So let's do that. Let's bring that down here. And now we have an expression for the potential from the radius inside the cylinder to a point outside at A. So now if we just integrate this, the final answer we're going to get is equal to Q over 8 pi the permittivity of free space. So all we need to do is just bring out the constants and then integrate it with respect to R. So it's really simple. And it's self-explanatory, so I don't think I need to do it. And now since these are just constants and it's there in both the equations, you can just factor it out, and then it's 3 minus R squared over R cubed. So we let VR equal the electric potential outside the sphere and at the distance R from the center. So in this case now, when it's equal to, so in this case we're gonna have to write a new potential for this second case, EdR. So now we can EDR. So now we can replace E by this, and we can bring out the constants to make it easier for ourselves. So 4 pi times permittivity, and now it's from A to R, R to A, and it's 1 over R squared, integrated with respect to dr. So now if we integrate this, we're going to get that it's equal to 1 over 4 pi times permittivity of free space times negative 1 over R with the constraints of R and A. So now if you substitute those in, we're going to get that it's 1 over 4 pi times the permittivity of free space and Q over R. And so that's the potential outside the sphere. Now if you were to draw the graphs, we just go ahead and do the potential versus the radius. So in this case, it would look something like this. So the peak would happen at the radius of the sphere, and then it will slowly decrease in value as it moves further away. And now the electric field would have a very similar graph, except this time it'll start from a lower constant value, and it would peak again at R, and it would decrease at 3 as it moves further away. Here, this looks like it's part of part A, so let me just make that clear. So this is the graph of E versus R. And that's it for this